All right. Well, back again, and now we get to try our best to understand more of this frame understanding and how to set problems up using the relativistic regime. So the statement reads that in part A, in example 12.6, we found how velocities in the x direction transform when you go from s to s prime, or s bar. Derive the analogous formulas for velocities in the y and z directions, respectively. Part B. A spotlight is mounted on a boat so that its beam makes an angle theta with the deck, figure 12.20. If this boat is then set in motion at speed v, what angle theta does this individual photon trajectory make with the deck, according to an observer on the dock? Okay, so we got two different points of interest there. What angle does the beam illuminated, say, by a light fog make? Let's compare this to problem 12.10, where we had a boat moving in the mast. All right, so let's revisit what that problem looked like. Here we had the observer on the dock. We had the beam from the spotlight, and instead of a mast, we just use a beam here. Again, same angle theta, moving to the right. We get everything we need here. Be careful how we define everything, but nonetheless, let's dive in. So in our solution, we know that in S, it moves a distance dy in a time dt. Now in S bar, meanwhile, it moves a distance dy bar in dy bar equal dy in time dt bar equals gamma. Again, this is from the Lorentz transformation rule for time. So we have t minus v squared, v over c squared with the position here. So with the derivative notation or the dt notation, we have dt bar equal gamma times dt minus v over c squared dx. And we'll just let that ride through. Here, what we could do is factor out a dt from both of them. So if we're to factor the dt out here, we have to put one under the dx. So that's what we do in the next step. And we're good to go. This force factoring method's been used the whole semester, so be aware of it. And then with that, since we know what we want is dy bar over dt, dt bar for s bar, now we just put the two over one another in terms of our regular derivatives. So we're left with dy over gamma dt 1 minus v squared over c squared v over c squared ux, since that's the velocity in the x direction. Since we don't want to use v, since v is the speed of which the object is moving. But nonetheless, here we know that we can bump this dt into the numerator, since when we have a fraction in the numerator, the denominators join together. So that's what we do there, and we show that we have u bar y is equal to u sub y over gamma times 1 minus v over c squared ux. And the analogous part to that is just change the ordinary velocities with z instead of y, and we're good. Again, this is assuming that the motion is in the x direction. Now, as far as part B goes, let us define S be the dot frame, and let us define S prime as the boat frame. Again, the prime, bar, whatever notation you want to use, is for the moving object. So what we actually need is the reverse transformation, since what we have is on the moving object and we want to get it to the stationary one. So here v goes to negative v. Okay, that's what we see there. Moving forward then, what we showed was that tangent theta from our old question, well, if we're looking at velocities, we see that the y over the x, so the adjacent, the opposite over the adjacent velocities will form this for us. That being said, we got to be careful about that negative sign, so be aware of it here. And let's plug everything through, let it simplify down. What's wonderful about this monstrosity is that with the Einstein velocity rules that we have for the part up here and down here, since we're not moving, and we know what uy is from the transformation that we just found, but ux just uses the Einstein velocity rule. The denominators cancel, so we're just left with a uy, gamma, and ux plus v. Hence, this simplifies down really nice. Again, be aware that this is the bar notation that we have in the tangent formula. Now, in this case, u bar x, since we know what we're seeing on the ship, is equal to negative c cosine theta, and u bar y is equal to c sine theta, bar, of course. So let's plug them all in. And this was why we knew to use u bar y over u bar x, was because of the relationship between sine and cosine. That makes sense. Let's plug it in and see what we're doing. Let's cancel out the negatives that we see here after we factor out a negative c in the denominator. So this negative c cancels with the c in the numerator and cancels the negative that we had from setting it up. And so what we're actually left with is 1 over gamma times sine theta bar over cosine theta bar minus v over c. Now, if we were to compare that to the tangent theta bar that we found in problem, tan theta that we found in problem 12.10, then we see that tangent bar was equal to gamma of the sine bar over, tangent was equal to gamma tangent theta bar, which we just broke into sine and cosine bar. That being said, that's how the velocity vector of an individual photon transforms. But the beam as a whole is a snapshot of many different photons at one instant in time, and it transforms the same way the mass does.